or maybe on the way in next 15 minutes, as I'm going to use the notation now explicitly. So now I'm asking the question, I want to write down the condition of ESS more technically. And by more technically, I mean now I'm going to go to more general strategies. I want to include mixed strategies. We are going to discuss what mixed strategies mean. But for the time being, let's say hypothetically there are mixed strategies which will be denoted by P, Q and all those. So if I have resident with strategy P, okay, and a mutant comes with strategy Q, to know if P is ESS, if I want to ask this question, what is it that I have to do? I have to calculate expected payoff of what? When P interacts with P, it gets a payoff given by this notation. With what probability P is going to interact with P? 1 minus epsilon, because epsilon is the fraction of mutants which has come in. The rest of it will be U, where P interacts with Q, because mutants have appeared with probability epsilon. This has to be more than what mutants are going to get against P with 1 minus epsilon, because P appears with 1 minus epsilon, and epsilon U Q against Q, because Q, you compare with what is there on the other side of the board, where when you have P and Q as 1 0 and 0 1, you get that expression where U 1 1 is R. So this is the special case of this, where P is 1 0 and Q is 0 1, right? So if you put it in here, you get that back. What is the argument going here? I want to know if the mutants appear, do I get an expected payoff which is greater than what the mutant would get as an expected payoff? Remember, the players are not C or D, those are actions. We are choosing an as if argument that players can as if choose their phenotypes, okay? But it is hardwired by nature, you are really not choosing it. You are sort of asking, if I arbitrarily go to a population and pick one guy, that guy could be of either this strategy or that strategy. So you are okay with this notation? So if that is the case, ESS, this has to happen. So what is the ESS definition then? You are going to have the dominant contribution is going to come from 1. So for ESS, you have UPP greater than UQP. If this happens for all Q, okay, not equal to P. So it should happen for all possible mutants, okay? Because if I am resistant towards a certain mutant, but not against some other mutant, I am still going to get killed away. So for all Q not equal to P, this has to be true. But suppose, okay, suppose and if UPP is equal to UQP for some Q, then what do I do? Because now these two are equal, so of course I have to check the other part. Then what has to be is U P against Q should be more than U of Q against Q. So physically you are saying whatever you get against the mutant should be more than what mutant gets against the mutant, okay? And for certain technical reason, because this weak Nash thing can sort of mess up, this equality can also be placed here without any problem, because all you are saying is either it's greater than equal to, and whenever it's equal, I am anyway going to check this. So this definition, this is called first principle definition of ESS. This is Maynard-Smith Price definition, and they are equivalent. We have come from here to here. You can also prove the other direction. Okay, so it's if and only if connection. I'll write the third definition, which is going to be important for us, but I'm not going to prove it. I have kept the last lecture for doing all kind of miscellaneous things if we get time. Otherwise, it's all about proving a simple theorem, and this is called Hofbauer Schuster Sigmund definition. By the way, when I talked about this epsilon, I did not say what is the value of epsilon. So you basically say here that there exists some epsilon which is less than some threshold epsilon. Okay, or rather, you should write more technically as this. There exists some epsilon such that for all epsilons between less than epsilon bar, this is true. You're basically saying you have a neighborhood about epsilon, some values epsilon, it's going to work. Okay, and you keep it vague depending on, because the reason is simple. Mutants are very rare, very small. So smaller the better.
So if epsilon is more like
yeah, if it's more, it's even good.
Like 60-40.
Yeah, that relation may just not work.
This first condition also
may not work. I want it to work for smaller enough epsilons. This is physically different, yeah.
So you're saying that if that condition is true, then the state.
No, I'm saying it in full, in its entirety, that if I can find a bound epsilon bar such that below that whichever epsilon you take, this condition is going to hold true. But I'm not saying what this bound is. This bound could be 10 to the power minus 9. This bound could be 10 to the power 9. I don't care. Okay, and 10 to the power 9, 10 to the minus doesn't make sense because epsilon has to be between 0 to 1. Right? If it's sort of 0.99 or 0.01, I don't care. Bigger, good, but anyway, physically small ones are going to make sense unless you get into cultural evolution and other things where suddenly you can get a huge chunk of mutants coming in. But in biology, no. Okay, so what is that theorem? That essentially says, there is the third definition of ESS, and that is going to be most important for us. It's equivalent. It is sort of saying that U P Q should be greater than U P Q Q in some neighborhood of P. This looks like this, but there is huge difference because these things are true for all Q, all mutants. Okay. But here you are saying I have a residence strategy P, the mutants can be only in the neighborhood of residence strategy P. Okay. And this holds. So there is a mathematical equivalence, one can prove that this becomes this becomes this becomes, they are all equivalent. Okay. But intuitively sort of it makes sense to you probably, because you are saying that if P is getting more payoff against mutant compared to what mutant can get against mutant, then definitely sort of P is growing up. Okay. But this is not that obvious, this has to, yes please.
But what is the,
yeah.
Is the Hofbauer-Sigmund
definition? Yes, it's same. Because I tracked on the papers, I figured out they were probably the first to give this schema.
In the other argument also we argued essentially the
Same thing. So you see that's the catch. The problem is I don't want to make incorrect statements. So let me rather make a correct statement without justification at this point. Okay, the proof, because you see, it's going to be a bit mathematical with the proof and all. If required, we can do it later, or maybe who are interested, we can do later during tea or break. Okay.
So in some neighborhood of
Neighborhood.
so you are taking P as like what do you mean by neighborhood?
Yes. Good question. Now that you have done nonlinear dynamics, if you want to talk about phase spaces and all that, where do you think probabilities reside? So if you have a probability, you see, they are consciously, I have not written any scalar PQ. I have written on vector PQ because these definitions are general, even for multi-action plays. Okay. So this is sort of the general definition. Now, if I have a vector P, which will be P1, P2, P3, P4, and all that, up to Pn, let's say, arbitrary vector, what is the space where it lies? So if you have a single P, okay, by single P I mean you have only P1 and P2, then of course it has to be something on the line, because once P is fixed, 1 minus P is fixed. So your entire space of probabilities will have the support, I mean the most general support possible is the line. But suppose you have P1, P2, P3, then where does the probabilities lie? It will be a two-dimensional, just one-dimensional less. Remember, here there were two probabilities, and it will be one-dimensional. And that will actually be, think about it, be a triangle like this. Okay, if this is axis, one axis, second axis, third axis, it will lie in this triangle. These structures have named, these are called simplex.
The triangle is
for three segments. P1, P2, P3, let's say.
So what's a simplex again?
Simplex is the structure. So simplex is a set of points such that the coordinate of, I mean I can write mathematically, but just in words, simplex is set of points such that the coordinates of the points have values between 0 to 1, and the sum of all the coordinates is equal to 1. That will automatically give you this triangle, this line and all. So when I say neighborhood, mathematically what I mean is, so if I am in 1D, I mean 2 P's, which is 1D space, if this is P, then mathematically the Q can appear only in the neighborhood. If I am in this space and this is my P, then it can appear only in this neighborhood.
in like 3D, I think you have a triangle.
That's what I have to do.
No, like in 2 dimensions.
2 dimensional. You have single variable. There is only one independent variable. In two, I mean, if you, what do you mean by 2 dimensional?
Like a triangle in 2 dimensions.
What do you mean by triangle in 2 dimensions? I'm confused. What are we talking about?
Like if you have so if you have like P and Q, like you have these two.
Let's not confuse Q here. I have a P where P has those elements. I'm just trying to denote P somewhere in some space, which will be the most appropriate space. If I have only P1 and P2, there is only one independent coordinate, which I am denoting by P. That P can run from 0 to 1. So my space is an interval, 0 to 1. If I have 3 P's, P1, P2, P3, then I have a 2-dimensional surface, because some of those have to be constant. And that surface happens to be this triangle. That can be very easily seen actually. You try it out as a homework maybe. This is the triangle. And then if you are in triangle, any other point on this, if I want to choose any probability which has 3 components, they all have to lie on this. And hence I can define a neighborhood of that particular P. So in that sense neighborhood, but actually I don't have to get into definitions much. All I am saying is you choose the coordinates such that they are close to P. If this holds, then this works.
So the reason why this is such an important, I guess, is that you are going to say that it refers to the stability of P.
Yeah, the mathematical proofs will use this definition of ESS. Yes, precisely, because I'll talk about local stability, global stability. So, these definitions I cannot work with, but this is the definition which is I going to work with. Okay. So, for the time being you have sort of the idea of what ESS is. All I am trying to sort of asking you to believe is this also works, otherwise I have to do the proof, that is all. I do not want to get into proof at this point of time. Okay. Right, and this is what it is. So, ultimately sort of this question mark now I want to get rid of, and I want to say rationality is driven by evolutionarily something, stability. So, rationality is basically being driven. Earlier you wanted to be rational, and by being rational you wanted to maximize your expected payoff and all that. Now, evolution basically is driving everything through the concept of evolutionary stability. You want evolutionary stability. Okay. We will do an example, it will become clearer over time. I mean, for the pure strategy we have already done the example, right. We did the prisoner's dilemma a little while earlier, but now we have to get into the more important part, which is trying to figure out that what does mixed ESS even mean, and how would I calculate a mixed ESS. Now, a very important thing which you can note from this definition, this Maynard-Smith-Pride's definition. Suppose you have a Nash. If you have Nash, then isn't ESS being implied? Because what is this? This is the condition of Nash in mixed strategy, right? P against P gets more than or equal to your strategy getting unilaterally deviated against P. So, this is nothing but the Nash condition. If you have strict Nash, which means only inequality is satisfied, you do not have to go to the second part of the definition. So, that means if you have strict Nash, it always implies ESS. Strict Nash implies ESS. If you have ESS, then either greater than or equal to is satisfied, right. But in addition, certain other things have to be satisfied. So, in addition, for the ESS being Nash, mixed or strict, it also has to satisfy something else. That means ESS implies Nash, but not every Nash is going to imply ESS, because there is an extra condition. So, ultimately what we have proven here is strict Nash implies ESS, ESS implies Nash, right. So, that is an important thing, and you have to keep that in mind. Strict Nash implies ESS and ESS implies Nash. When I say Nash equilibrium, I mean any kind of Nash equilibrium, mixed, pure, I do not care. But strict just means the equality is not satisfied. Where is it? So, this is the condition of Nash, right. In any game theoretical inequalities, when equality is not included, that is called strict, and when equalities are included, that is called I mean that is not strict, I mean it is a weaker equation, that is all. Strict just means equality not being there, right. So, if equality is not there, only first condition is enough for definition of ESS, because I do not go into the clause of if, hence strict Nash defines ESS. But once I get into the clause of if, then definitely it has to be Nash, but in addition something else. So, hence any Nash cannot imply ESS, because this condition is separately required, but ESS has to imply Nash, but if it is strict, it is definitely ESS. So, this is one of the very important relation, and that tells you why mathematically Nash is a very important quantity to have in such a setting. Because if somebody asks you, just like that Netaji said, I give you a matrix and I ask you, take matrix, give me ESS. In principle, you have formula. Even without knowing about evolution, biology, psychology, philosophy, if you know maths, which is probably easier than those things, you can find out ESS. So, there has to be a proper way of calculating ESS, and that is following these definitions, and this is much more cumbersome than finding only Nash. So, this comes to help. This tells you ESS has to be Nash. So, what you do is first you find out Nash, then you check whether that Nash is ESS, because otherwise you have to check for every P to figure out where is ESS, which is not ESS, right. It's so at one stroke you have eliminated many of the strategies, and you only have to check for few strategies which are Nash. So, the step of calculating ESS is going to be first calculate Nash, then find out if the Nash strategy follows these definitions, and you are done. I will give you some other facts here, which again sort of requires some mathematical proof we are skipping, that interior ESS is the only ESS. What I mean to say is, by interior I mean, when I say these things interior and all, I am actually in the geometric picture of probability space, okay, not in the sense of Kolmogorov probability, in the sense of that geometry just. In that space, if the ESS is in interior, what would it mean? ESS is what? ESS is a strategy. Strategy can be pure or mixed. Any strategy which is in the interior would mean it is not pure, okay. It is not even on the boundary, it is right in the middle somewhere. There is a theorem which proves that if you have found one ESS in the interior, there can be no other ESS. So, that is good thing. Somehow you ended up finding 10 Nashes, you picked the interior one that ended up being ESS, you do not have to check for any others. Okay. If you have ESS which are corners, then that is possible. I mean, this corner, that corner, you can find ESS like that. I mean, the technical statement is, I do not want to get into that, but sort of technical statement is that if there can be two ESS which do not share their support in probabilities, okay. If it did not make sense, forget about it, just remember that, we can talk about those things later, okay. So, there are many things how to calculate ESS which comes into being, and this also says sometimes ESS may not be there, cannot be there. The Nash's proof is not for ESS, so ESS may not exist, okay. So, right now what we are discussing at this point is, just to summarize, that if I want to calculate ESS, I have to find out whether it is a Nash, and then I have to figure out whether the condition holds. If by chance that happens to be a mixed strategy Nash, I do not have to look for anything else. That will be the easiest way of calculating an ESS. Okay. So, any questions here? Otherwise, we go to an example to show how this is done. No, not possible. Oh, multiple interior? Multiple mixed strategy Nash. I can't remember. Well, actually not. Well, yes, it can be, but it has to be degenerate. It has to be line.
Okay. Right.
That can be there. But isolated Nashes not possible, because I am solving set of linear equations to find Nash. So, there is a unique solution only for linear set of algebraic equations. So, should we do an example, or should we discuss what mixed strategy even means in ESS? You are not willing to work if you do not know the reason why you are working, or you are willing to work. Well, if this was the midterm, if there was a midterm exam just tomorrow, then example would make more sense. No? That would be an important question which should come next time. But here we have the liberty of. So, let us maybe discuss a bit before going to examples, that what does even mixed strategy would mean. So, remember on the very first day when I was doing all the bullshitting, there was a very important thing which I said, that how do I know that I myself am not a randomizer within? And I was talking about behavior. You see, behavior itself is a strategy. There is huge question on why do we even have emotions. If you think about it, emotions would have an evolutionary reason, right? If there is a snake and my emotion is not to get scared, mostly I am going to get killed. By curiosity, I will go to a snake. But if I have the emotion of being scared, I am first going to run away. And then probably my secondary neural circuit will kick on, which will take me out of the phobia, and sort of I will go there. So, your behaviors are definitely evolutionary hardwired into you. So, can you have behaviors which can act like mixed strategy? Okay. There are many examples, okay, human world. So, there is a example which you will find in many places. It's called great, I think great golden digger wasp. I mean, the English name is hard enough, scientific name don't ask. So, what does this wasp do? So, let us say it wants to lay eggs. Now, it can have two strategies. One is it basically digs hole and lays egg. The one thing is the wasp can actually dig hole and lay egg. The other thing is the wasp can actually find another wasp who is staying inside hole and would fight that wasp off the hole and lay egg there. So, now there is a sort of what to say, competition going on in your mind, whether I am going to spend energy in digging the hole or fighting off the wasp. Okay. And it is seen that these wasps do it with a certain probability. Okay. In a way that, let us say, I do not remember exact details, but it goes something like this, that let us say I am going to dig with probability 40% and I am going to fight with probability 60%. So, this is a behavior in itself, and this itself can be genetically hardwired, because most wasps would be doing the same. But suddenly suppose a mutant wasp comes who is like digs with probability 50% and evades or fights the wasp with probability 50%, that is a different kind of behavior. These both behaviors have been created from the pure actions of digging or fighting. But you cannot say that these behaviors do not exist, and it is like I am only going to do one at a time. Of course, you are going to do one at a time, but your behavior is of a mixed kind. So, in that sense, mixed strategies can exist. Of course, certain mixed strategies are not possible. I cannot be black and white at the same time with some probability. Not every mix of pure strategies can facilitate mixed strategies, but certain can, mostly behavioral ones can.
As an individual,
Yes.
so can you make a decision like I will fight 60% and take 40%?
That is the thing. This is a behavior which is neurally sort of hardwired. We do not know how this has happened. But when you take the statistics,
I mean, I think it's more like at each instance it's deciding whether to fight or.
of course, but with some probability. It is the soul of the wasp.
Yeah.
That is the behavior. Where is that probability residing? I do not know, but that is the wasp's behavior. And I want to categorize that behavior or tag that behavior mathematically. What would I do? The only tool I know is probability. So, I am categorizing that behavior as 40, 60, digging, fighting. You can say I am formalizing this because I have no other tool how to categorize this behavior.
Would you call codominance a part of mixed strategy?
You have to explain a bit more. This codominance, well, in the sense you are saying the alleles and all that. Yeah, maybe. Of course, in as if sense seems like at first, but we will discuss a bit more before I make useless statements. Okay, so all I am trying to tell you here is that of course mixed strategies are possible at behavioral level at least, not at hardwired sort of very fixed phenotypes and all. That is not possible. But evolution is, I mean, think about it. There's a very nice example. This I don't know where I read. You know of Lamarckism, of course, right? That how giraffe's neck got tall. The one of the arguments was that a giraffe would keep trying to eat leaves which are higher and higher and higher, and with that the necks would get stretched, and that is going to pass on to the generation. And then people said, okay, this is not how it works. Darwinism sort of wins. There is a sudden revival of all this thing. This called neo-Lamarckism and all that. No? And these are all can, I mean, some of them can be connected using something known as Baldwin effect. Okay, some of you may have heard. There is a nice example where I think this example was, you can find it in YouTube. There is a video by Dawkins. So he was sort of saying, now I may be wrong in details, but it's like, you know, those movies where you say, you know, there is no connection with the, just to be safe that you are saying nothing wrong. So there apparently in 70s or 60s, there was this thing that, you know, the milkman would deliver milk in Britain in bottles, and they will put the bottles in front of the door. And there used to be a certain kind of bird which will come and try to have the milk. And over time what happened, that some birds learned to open the thing and they would drink it. And then over time it was seen that almost all birds are starting to do it of that species. So now you can think of two phenotypes, birds who can open the cork and the birds who cannot open the cork. But just by, you know, the birds who were sort of doing all this sort of spread out in the population. So the explanation which comes through this Baldwin effect and all is something like this, that what is action here and what is sort of evolutionary important here is how fast a bird can learn. So some birds would learn fast, some birds would learn slow. Those who are going to learn fast are going to pick this up, and the faster a bird learns, the better the bird sort of becomes at it, and once it learns so fast that you start calling it an instinct of a bird. So instinct is basically learning mechanism learned extremely fast. Okay. So because the enigma was that, you know, the birds are learning in the lifetime. How come their kids just after getting born are also doing this thing? How are they learning and all that? So it's the learning mechanism which is sort of got evolved from one generation to another generation.
So can we maybe control these probabilities with some sort of like Pavlovian treatment, where we actually
Maybe.
yeah.
Maybe, but the problem with Pavlovian at a historical and philosophical level is Pavlov was very much into non-existence of soul. He only believed in reflexes. So, I mean, some behaviors would be modeled by reflexes, but some will not be.
But if you do it enough times, won't it be kind of hardwired to the?
I don't know. I mean, these experiments are very hard. Okay, and there are only few examples here and there. That too, there are alternate explanations. Now you fight off. Right? But the beauty of game theory evolution is that it is all pervading in a sense. You have a single mechanism to understand everything. Right? Okay. So now coming back, let's do one example. Yeah.
So instead of saying how the kids of these birds are learning so fast,
Yes.
so this learning behavior is transferred to coming generation. You could say that there was some neural mechanism which helped the birds to learn this.
Yes.
And
That
instead of
got-
they are getting food that got selected.
Yes. That's what I am saying in a way. Ultimately, by learning mechanism, I meant that neural circuit. But these are all vague. Nobody has pinpointed what is where. But that's an explanation. Exactly. You are spelling it out in more detailed fashion. Learning basically would mean some neural circuit somewhere. That's what the belief is.
No, I meant when you said how these baby birds are learning so fast.
So that's what you are saying is exactly what I said. I said it in one word, learned. But what does learning fixing mean? In some neural circuit, something has happened. No? Some circuits are going to help you learn faster. Some circuits, that's the belief. I don't know how people pinpoint it. I have no clue. So let's do an example now. I give you a matrix 3, 5, 1, 0. And I ask find ESS. Anybody recognizes this game? It's the hogged off game. Because if you try to calculate Nash, because that's what we have to do. If I want to find ESS, what do I have to do? I have to find Nash first and then see if Nash works. So what are the Nashes? This is not Nash definitely. So the first strategy is not Nash. Let me call C D if you want. Is C Nash? No. Is D Nash? No. Incidentally, C D is Nash. But remember, we are only working with symmetric metrics because a symmetric one in our formalism makes no sense. Is there an interior Nash? Let's see. So to find interior Nash, what do? We put something like P 1 minus P, then we do 3P plus 1 minus P, and this is 5P, and 5P equal to 3P is going to be equal to, sorry, what do I want? Yes, I want them equal, right? So that implies P equal to 5 to, is there something wrong here? That's fine, no? Yeah, it's not probably giving what I wanted. Yeah, it's 1 by 3, no? Okay. So Nash is 1 by 3. That's the mixed Nash. Now I want to know whether this is ESS or not ESS. What would that mean? That I have a certain behavior where I pick C strategy with probability 1/3 and D strategy with probability 2/3. Is such a strategy resistant against any other mutant, where mutant can pick a different combination of playing C and D? This is what you are asking. This was the formalism. It said find Nash first and then check whether the formalism works. We have found its Nash. So let's check how it works. Now, since it is mixed strategy, automatically it has to be weak Nash, right? I mean, if you want to explicitly check, we can explicitly check. So let's go with Maynard-Smith price condition. That's the easiest to check in matrices. Okay. So what do I want? I want to check whether UPP is greater than or equal to UQP. Now, because I am working with only 2 action game, UQP, no?
Which definition I mean?
Maynard-Smith price. So I am no longer putting vector because I am working with only 2 action. So the scale, the first component of the vector is enough to define my U. Okay, so I am writing it like that. So how do I check? So PP, I already know what my P is, which I want to check, is 1/3. So it's going to be 1/3, 2/3. The matrix is 3, 1, 5, 0. Your P is 1/3, 2/3. This I want to see if this is greater than equal to, Q is going to be arbitrary because it has to be true for all Q's, and this is 3, 1, 5, 0, and this is Q 1 minus Q. Okay. So what does this give?
1/3.
1/3 and 2/3.
Yes, yes. Thanks. So this is 1/3, 2/3. So this multiplication is going to give me 3 times 1/3 and 2 by 3. So that is 1 plus 2 by 3, 5 by 3, right? And this is 5 by 3. Is this greater than equal to Q 1 minus Q This multiplication we have already done on this side, same multiplication. So 5 by 3, 5 by 3. Now, if you multiply this, what are you going to get? 1. That side also you are going to get 1. So, they are equal, which is what it has to be. Remember, if you have a mixed strategy Nash, then definitely payoffs are all same. It does not matter what you take or not take. So, automatically it is equal. But if it is equal, I have to check the next one. Okay. Sometimes it will be that it is equal for some q and greater than for some q. Then I check only for those q for which it is equal. But here it is equal for all q. So, I have to check for, now I have to show that this holds for all possible q's. Okay. So, let us check that. So, I want to show u p q is greater than u q q. And what do we have? This one side we have, okay, none of them we have done. So, 1/3, 2/3, 3, 5, 1, 0. This is q 1 minus q greater than q 1 minus q 3, 1, 5, 0 and q 1 minus q. You can also do on your own and we can match what we get at the end of the day. So, this is 1/3, 2/3, 3q plus 1 minus q, 5q, 3q plus 1 minus q, 5q. So, this will give me 1/3. So, 2q plus 1 plus 10q by 3 3q. So, this is 2q square plus q plus 5q minus 5q square. Right. Okay. This goes 3q square minus sign 6q. This gives me 12, 4q plus 1/3. So, 4q plus 1/3 is greater than, please let me know if I have already made a mistake. Okay. It's going somewhere. So, then this goes, it's 2q. Yeah, I think it's okay. So, I have 3q square minus 2q plus 1/3 greater than 0, whether this is true or false, right. And if I take 1/3 common, then basically this is 1, this is 6 and this is 9, and hence I have 1/3 times 3q minus 1 whole square. And of course, a square is always going to be positive, and hence the condition is true for any q. Okay. So, of course, this strategy in the Hogduff game is an ESS. So, this is how one has to check. It becomes more and more complicated as the size of the matrix becomes bigger and bigger and bigger. Okay. But it is made easy if you already know what Nash is, because then it becomes all the matter of checking the conditions. So, you can automate it and put it in computer and just ask to do symbolic calculations. Okay. Any questions here? We will now change gear a bit. So, if you have anything in this module, please ask. The calculation is okay? There is nothing in there actually. So, let me. Now, we can ask a even more difficult question, which you could have asked or you must have already asked when you were doing classical games. You see, I give you a matrix, you find me solutions. If I take this and I say that where this will be, what are the equilibrium positions, you will say, well, this is an equilibrium position. If I do it like this, and if I were to able to keep it exactly like this, definitely it is an equilibrium position, the forces would balance out. But if somebody asks you that somebody is playing with umbrella, is it going to settle down here or is it going to settle down here? How are you going to find it out? Because existence of equilibrium does not mean that thing exists. Think about the mechanical world. Your mechanical world, you exist, this board exists, sort of this bag is here, this is here, simply because these are all in stable equilibrium. Anything which is not stable equilibrium, you cannot see for eternity. They will settle down somewhere else. That is the reason in nonlinear dynamics we are very much interested in stability of solutions, just solutions are not enough. So, in the case of umbrella, you would say, well, I can figure out whether I am going to see an upside down umbrella or down down umbrella is by going through Newton's laws, and Newton's laws are going to tell me, well, where it is going to settle down in equilibrium. Now, you did prisoner's dilemma game or something, you found out, well, being defecting is a Nash, but somebody asks you, how are you actually going to go there? You have only proven that the solution exists. Right? It is like playing carom board. Every time I play carom board, I actually know where to hit to put the puck in the pocket, and I am never able to do it. I know solution exists, but I never win. So, you know Nash exists, but are you going to play Nash? How would you go to Nash? How do you do calculation about Nash? Something is going in your head. I do not even know what equations are going, because I do not know about the neural circuits and all, what are sort of activating, what are not activating, but some arguments are going on in head at some level. What about evolution? Here also you are saying ultimately I want ESS, but are you sure you are going to go to ESS? It may be it is just a mathematician's construct, actually nature goes somewhere else, the dynamics takes it somewhere else. So, just having a solution concept is not enough, we definitely need to know whether we are going to solution concept, and that tells us we need some kind of a dynamical equation which will take me to the solution concept, and that the solution concept better be stable under that dynamics. Only then I can see it in nature. Otherwise, if I tell ESS exists and I tell an experimentalist go and do an experiment and find ESS, the experiment is not going to see it, because there are so many perturbations in the world, it will always drive the solution away from ESS if ESS is not stable. The fact that the word ESS has stable in it does not make it stable. Just because I name myself as intelligent, that would not make me intelligent. So, you want things to be stable. So, here comes the thing, the stability in the concept of ESS is not a dynamical stability, it is a game theoretic stability, an evolutionary game theoretic stability. But what is important in nature is you want to have a dynamical stability. So, now we need to write down an equation which at least makes sense under natural selection of Darwin. Okay, that is where we have sort of come to now. Now, this equation can be derived in many ways, starting from finite or phenomenologically this that. I am not going to go into there, because then we are just going to waste time in deriving it, and it is not going to give, as per me, any new insight unless you derive it from finite population using Fokker-Planck equation and all that. But that sort of advanced thing we are not doing it. So, let us keep it for the last lecture. In case we get time we will do it, but we can argue out an equation just in the fashion you were argued into believing SIR equations. Did you see any derivation? You just say, okay, this is there is a infected guy, you put a squared term, you put a cube term, write it down, and somehow it works. It is a compartmental models. So, let us introduce it like that and argue things out, and then prove the most important theorem in the evolutionary game dynamics, and that is ESS is asymptotically stable fixed point of the dynamics we are interested in. Okay. So, it will prove that if I have ESS, I will actually go there, and not only I will go there, I will go there sort of asymptotically, I am going to reach there at the end of the day. And we are going to see there were 2-3 concepts I saw that you heard in last few lectures. One is the scale divergence, Kullback-Leibler divergence, and you also heard about Lyapunov function in the last talk. We are going to see how this game theoretic concept can be understood as one of the fundamental principles of information theory and entropy using KL divergence and all. So, I will use the tools of information theory to prove that ESS is always asymptotically stable. Okay. So, let us write down the dynamics and then we go for lunch. No, I have 2 lectures, no? Oh, wonderful. You will be tortured like anything. Right. So, what is microevolution all about? You have fractions of types, you have a single species, you have various types of the species, they can be written down x1, x2, x3, x4, x5, sum of all the xi's have to be 1 by definition, right. And what is microevolution all about? These fractions keep on changing. That is what evolution is all about. It is not always the flashy thing of creating new species, although we will discuss that later in adaptive dynamics. So, right now microevolution. So, we are asking the question, what is the per capita growth rate of a particular trait? How should I write down the law for this? So, we go phenomenologically and we say we are going to follow the tenet of Darwinian fitness, Darwinian natural selection. And what did Darwin say at the end of the day when you sort of make it popularize it and all that? You say that, well, it is survival of the fittest. Now, what does survival of the fittest turn into in our mathematical statement? That the fitness of a particular type, if it is more than the average fitness of the population, then that fitness, that particular trait has to grow. That is all I want. So, we can now write laws in many complicated forms, but we are going to follow Occam's razor and write the simplest possible way we can do it. And that is, we are going to say, so what is going to be the fitness of I given an underlying matrix U, or let us say A. I will write A because of a reason which we will discuss later. So, if the matrix is A, just like the one we have written there, then what do? You have the x vector and you take its ith component, because that is what it meant, right. If you had x1, x2, x3 dot 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 xn and you have the matrix A, then you have x1 dot 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 up to xn. These things, forget about this part for the time being. When you have this thing, what does it give you? It gives you that you multiply all the rows with this and you are essentially getting, suppose you want to find fitness of this, what do? You multiply this row with these probabilities and you get fitness of this, which is nothing but the first element of this multiplication. For the second one, you get the second element of this multiplication. So, for the ith one, you are going to get ith element of the multiplication. So, this is the fitness of the ith trait. Okay.
In the denominator, should there be a summation?
Denominator, what do you mean?
Xi dot by xi.
No, we are asking per capita growth rate of a particular trait. And then we are asking if this is more than the average fitness. So what is the average fitness? This was the average because whatever I got, now I have to average over all other possibilities. So what you are saying is, if I pick an arbitrary individual, okay, when you calculated this, what was the question you answered? You answered, if I pick an individual with ith strategy, what is the expected fitness? That was this. Now you are asking the question, if I pick an arbitrary individual, what is the expected fitness? But arbitrary individual can be of any type. That means I have to average once more over all expected fitness. So it has to be average and then its average. That is going to be the full average of the population. And hence the term is, that's the matrix multiplication one has to do. Now it says if this is more than this is going to be positive, this is going to grow. If this is less than this is going to be negative, this is not going to grow. That's survival of the fittest. So we can phenomenologically write down this equation. As I said, there are many derivations for this. They are just going to be a detour. Okay.
Can you explain the average part?
Yes. Suppose I asked here, if I pick an arbitrary individual in the population, what is the fitness of that arbitrary individual? Now that arbitrary individual can have strategy C, it is going to get a fitness given by this, but the individual could also have been D, and then the fitness would have been this. With what probability you are going to get this fitness? The probability with which you were C, which means you have to multiply this with P and this with 1 minus P, which is nothing but this multiplication, second multiplication. So this proportionality constant can always be taken into time and redefine time and all that. So you just put it as an equal to sign, you write this as xi. This is a replication selection model. This is called replicator equation. This was given in 1978 by Taylor and Jonkers. Now there are certain things you should observe first about replicator equation before getting into it. This equation does not allow for any mutants. Right from the beginning you are saying you have distribution of traits. All you are interested in how the trait frequency is changing. Note your fitness is dependent on frequency. Hence you are actually into evolutionary models, right? Remember that subset set we had drawn? On top of it, you are selecting the trait which is more fit compared to average.
And is this in each time step? Like
Yes, so dot means DDT. Yeah, so this is DDT, time step means DDT. I have written a continuous equation. I could have also written down a discrete equation and all that. This will be easiest to work with for the time being.
So the proportions here are the proportions within a population.
Yes.
But these factors are supposed to be our mixed strategy. It's not this.
Yes, that's a good question. That's where I was coming. Okay. That's the reason I used A, not U, like earlier. Okay. There is a catch there. I'll tell you in a little while. So the population is not changing anymore. Population has got fixed at some demographic attractor. It is not changing. Okay. Only the fractions are changing. There is no mutant here. Okay. And because there is selection going on, it's also has selection dynamics. And because after selection things are increasing, you are also replicating. And this mechanism of replication is at every time step, which means it goes from one generation to other generation. So you are right in the middle of the Venn diagram which I had drawn. You have evolution, you have selection, you have replication. So, that is why it is a replicator equation. It is the strongest form of evolutionary dynamics which you could write. You can make it weaker and weaker by taking down the effect step by step. Okay. You cannot just create any mutants here. If you were to create, you have to put some term where mutants appear. There is nothing like that. Okay. Now, this is this very important question she asked, that here suddenly I am talking about fractions, there we are talking about mixed strategies. What is it suddenly we have done? Okay. Yes. Yes. Good. That is why I am thinking whether I should explain it or not in more details. It will take half an hour. So, okay, let us do it.
How are you tracking the change? Like, that's what I don't get.
Tracking the change?
Like, so dx by dt.
So, dx by dt is what? Dx by dt is nothing but xi at time t plus delta t minus xi at t by delta t, limit delta t tending to 0.
Yeah, yeah.
Is this the change?
Yeah.
So, that is how you are sort of putting it in here.
No, but how are you getting that difference between time steps in that in the RHS?
In the RHS?
Yeah. Because I understand it. It's just the proportion of xi over all x's, like fitness, in one time step. Where is that dt coming?
Okay. Okay. Don't take it as an offense. I just want to know how to explain it to you. What is your background?
Economics.
Economics. Okay. So, let us do it in economical way. You see, let us start with the discrete thing, the way I think it will be easier to understand. Let us say I had at a certain point of time a trait frequency xi. Let me put the tag t. Okay. I am doing it discretely. I want to know at time t plus delta t, which I am just calling 1, the next time step, what does it become? This is what I want. I want a connection. So, I need something which is going to either grow it or decay it. Because this is discrete equation, I am going to do it in this fashion. I am going to say this is my expected fitness. Okay. Maybe I should put vector. And if this expected fitness is more than the average fitness, I am putting it in denominator. Do not get confused, I will come to that. Okay. Let us take it anew. So, if this expected fitness is more than the population average, this will be more than 1, this will be more than whatever xi was, and this will be more. This works with you, right? Now, I want to make it differential equation. So, I track the change. I can do it, subtract and add, right? So, this is nothing but now delta xi, you can say at time t, and this is what it is. There is a denominator here which has to be taken in somewhere. It is actually not correct the way I am putting it, because this is not that, this becomes adjusted replicator equation which has other properties, but that tells you the idea roughly. So, that is what is sort of happening there.
So this A is the.
I am coming to A. Let us go to B and C and then come back to A. So, any B, C questions? My friends would kill me. No other questions? Okay. So, let us take detour, 20 minutes. Now, this is very important question. This is at the crux of another fundamental understanding of why evolutionary game theory works is called strong stability. Okay. He was trying to put it under the rug, didn't work.